Hi, I'm Chrissy. Today, let's take the mystery out of artificial intelligence. When your phone predicts the next word, a streaming app suggests a movie, or a photo tool recognizes a face, it can feel as if a machine is thinking. But is it? Not in the human sense. Most AI systems identify patterns in data and use those patterns to produce a prediction, recommendation, or response. That simple idea powers many impressive tools, but it also explains why they can make mistakes. In the next few minutes, we'll unpack how AI learns, explore familiar examples, and try a quick exercise that helps you think like an AI builder, no coding or advanced math required. Artificial intelligence is a broad term for computer systems designed to perform tasks that normally involve human intelligence. Those tasks might include understanding language, recognizing images, planning routes, or making recommendations. AI is not one single machine or universal digital brain. It is a collection of methods, each built for particular goals. A navigation system can calculate routes, but it cannot automatically diagnose an illness. A chess program may outperform expert players at chess while knowing nothing about cooking. You may also hear the term narrow AI. That describes nearly all AI in everyday use today, systems that are capable within a limited domain. Their performance depends on their design, data, testing, and the situation in which they are used. Machine learning is a major approach within AI. Instead of writing a separate rule for every possible situation, developers provide examples and an algorithm adjusts a model to capture useful patterns. Imagine sorting email into spam and not spam. A traditional rule system might flag specific phrases. A machine learning system can examine many labeled emails and learn combinations of signals, such as wording, sender behavior, and message structure. The trained model can then estimate whether a new email resembles spam. Learning here does not mean understanding as a person does. It means changing numerical parameters to reduce errors on a defined task. The quality and relevance of the examples matter because incomplete or skewed data can produce weak or unfair results. Building a model usually involves 3 stages. During training, the system processes examples and adjusts its internal parameters to improve at the task. During validation, developers compare versions and tune choices without using the final test set. Then, testing measures performance on separate data the model has not seen during training. That separation matters. A student who memorizes an answer sheet may score perfectly on those exact questions but struggle with new ones. Models can do something similar called overfitting. Good evaluation asks whether a model generalizes to realistic new cases, not merely whether it remembers training patterns. Teams may also test different groups, unusual inputs, safety risks, and changes over time, because one overall accuracy number can hide important failures. Once trained, a model can receive an input and produce an output through a process called inference. Consider a photo classifier. The input is an image represented as numbers describing pixels. Layers of mathematical operations transform those numbers, detecting increasingly useful patterns. The output might assign estimated probabilities to categories, such as cat or dog. The highest score becomes the prediction, depending on how the application is designed. A probability score is not certainty, and it may not be perfectly calibrated. Small changes in the input, poor lighting, or an unfamiliar kind of image can affect the result. That is why responsible applications consider confidence, allow human review when stakes are high, and monitor whether real-world inputs differ from training data. Generative AI creates new content, such as text, images, audio, or code, based on patterns learned from training data. A large language model processes language in small units called tokens and repeatedly predicts a likely next token given the context. By continuing that process, it can produce fluent paragraphs, answer questions, or transform writing. It does not simply retrieve one stored sentence for every prompt, and fluent output does not guarantee factual understanding. The model can generate an incorrect statement that sounds confident, often called a hallucination. Its response also depends on the prompt, available context, system design, and any connected tools or sources. Treat generative AI as a powerful pattern-based assistant whose outputs still require judgment and verification. AI often works quietly inside ordinary products. A music service ranks songs you might enjoy based on listening patterns and other signals. A bank may use models to flag unusual transactions for review. A camera app can improve focus, reduce noise, or organize photos by visual similarity. Translation tools estimate an appropriate phrase in another language, while accessibility software can caption speech or describe images. These systems do not all use the same model, and they do not perform perfectly for every person or setting. Some combine machine learning with handwritten rules, databases, and human decisions. When evaluating an AI claim, ask what specific task the system performs, what information it uses, and how success is measured. Specific questions cut through vague marketing language. AI errors usually have understandable causes. Training data may be incomplete, outdated, mislabeled, or unrepresentative of the people and conditions where a model is deployed. The goal chosen by developers may reward the wrong behavior, and input may fall outside what the model encountered before. People can also misread a model's score or use a tool for a purpose it was never tested to handle. Bias is especially important. A system can reproduce or amplify patterns of unfairness present in data or design decisions. More data alone does not automatically solve these problems. Better outcomes require careful data practices, meaningful evaluation, domain expertise, feedback from affected communities, ongoing monitoring, and a clear way for people to question or appeal important decisions. Responsible use starts with matching oversight to risk. For brainstorming a party theme, a mistake may be easy to spot and fix. For medical, legal, financial, hiring, or safety decisions, errors can cause real harm, so qualified humans and reliable sources must remain involved. Avoid entering private, confidential, or sensitive information unless you understand how the service stores and uses it. Check important claims against trustworthy primary sources, and disclose AI assistance when a school, workplace, client, or audience expects it. Watch for fabricated citations, stereotypes, and content that copies someone's distinctive work too closely. Finally, remember that AI output can support a decision without owning responsibility for it. People and organizations remain accountable for how these tools are chosen and used. Let's try a 2-minute exercise with objects on your desk. Choose 2 categories, such as useful for writing and not useful for writing. Pick 6 objects as training examples and label each one. Now invent a simple rule from the examples, perhaps shape, material, or typical use. Test that rule on 3 new objects, including one tricky item like a touchscreen stylus. Did your rule generalize or did it fail? Next, change one label or add a more varied example and test again. You have just modeled several core ideas, labeled data, a learned decision rule, unseen test cases, ambiguity, and iteration. Real machine learning uses mathematical algorithms and far more data, but this hands-on version reveals why examples and category definitions strongly influence results. Here is the big picture. Artificial intelligence is a broad field focused on computer systems performing tasks associated with human intelligence. Machine learning is one approach that builds models by adjusting numerical parameters to find patterns in examples. Training shapes a model. Separate validation and testing help reveal whether it works on new cases. During inference, the trained model turns an input into a prediction, ranking, or generated output. Generative AI can create useful content by predicting patterns, but confident language is not a guarantee of truth. Every system has limits shaped by its data, objective, design, and deployment context. The smartest question is not, is this AI intelligent, but what task does it do? How was it evaluated? And what happens when it is wrong? AI becomes much less mysterious when you see it as a set of design systems learning statistical patterns for specific tasks. You do not need to become a programmer to ask good questions, test a tool thoughtfully, or notice when an answer needs checking. This week, pick one AI-powered feature you already use and investigate it. What goes in, what comes out, and what kind of mistake could it make? Share your example and what you discovered in the comments. If this beginner-friendly breakdown helped, subscribe for more clear, practical lessons about technology without the hype. I'm Chrissy, and thanks for learning with me. Stay curious, protect your judgment, and I'll see you in the next lesson.